of announcements here on the board. So this is the second to the last time I'll see you guys all together for lecture. We'll talk about the exam here in a minute. So this week in lab is your last experiment. Oh my God, no, isn't it terrible? It's so sad. You guys should be like teary-eyed. Your last quiz. Your experiment 12 report is due. Next week in lab, we're going to have a data discussion, data comparison for experiment 14. So in lab lecture next week, I'm going to talk about a set of tables that you have to prepare for your data as well as other people's data for experiment 14. Make sure that you understand those tables. Make sure you come to lab lecture for that information and understand that, because before your lab period, you will need to prepare these tables and come with the information that is needed. So out of the data discussion, we'll have evaluations, we'll clean up and check out a lab. So all of this, these three guys, plan on probably a couple hours in lab for that, okay? Because the data discussion itself could be an hour-ish or more. So plan on, 2.5, 3 hours, depending on how long the data discussion of the things takes. Okay, it won't probably be a full lab period, but you will be in there for a good chunk of time. Then your experiment 14 report is due, so see your prof. All of us will potentially have different due dates for that. So you see specifically for your lab section when that is due. So final exam is 2 weeks from today. 2 weeks from today, you'll already be done. So on Monday, December 14th, from 12:30 to 2:30 is the final exam for Chem 255. Like I've been saying in previous weeks, we will all gather together, everybody all at once, in this room to take the exam all together. So this is the exam time, day and time for the 4 o'clock lab lecture, so we will all be in here together. If you receive special testing accommodations for your regular organic exams and want that for the final exam, you need to see me. I am the person that fills out the paperwork for the academic success for this, okay? So if that pertains to you, make sure you see me, and I want to definitely see you probably before next Monday, if not at lab lecture next Monday, okay? So bring your paperwork with you, but especially having a Monday exam, we need to take care of that no later than next Monday. Okay, I need to make one announcement about experiment 12, and then we'll talk about a couple things in then experiment 14. So experiment 12, I've had some questions about analyzing TLC plates. I want to make sure that everyone understands when you're talking about TLC analysis, and you have kind of the condition with TLC analysis that the way we use TLC, we were only seeing things that were UV active. But if you see one spot, that is going to show purity, okay? So if you have only one spot present for a lane that you spotted on your TLC plate, that means that that lane has something, it's made up of one thing for that lane, okay? Whether it's starting material or product, but one spot is what shows purity when you're talking about TLC, okay? So just keep that in mind when you're writing up your reports, okay? All right, so before I talk about Friedel crafts, we need to talk about lab notebooks in general and some incidences that happened last week with lab notebooks that were really concerning for the lab profs as well as other students that were involved. So apparently Tuesday afternoon, evening, lab notebooks that were returned from Dr. Gilmore. He had had students, they were able to turn in their notebooks Tuesday morning, and if they made that deadline, then he would grade them and return them for his students. Some of those notebooks were then used by other students to see how they were graded and look at their rubrics and look at the notebook and try and use what was in that notebook to improve what they turned in. So there's many levels of why this is concerning. First of all, foremost level is that's a violation of a student's privacy. And that's huge. hugely concerning for the lab profs and huge as far as campus policies, that you can't violate another student's privacy that way. So, so for the students involved, it was very upsetting that their work was then being used by other people to help improve them and not taking into consideration that student's feelings. There was no, like, they didn't get to give permission for that situation, okay? Another problem with this, besides that huge problem, is it's a violation of academic integrity. It is a method of cheating. So again, college policy is against that, okay? So what we have talked about as lab profs is we will be careful in how we hand back lab notebooks. We won't hand notebooks back to people until we know that all the notebooks for a given experiment have been collected. We have used the cubbies outside of the organic stockroom as a convenience for you guys to be able to have access to your work once it's graded, so that you can easily get to your notebook at any point, day or night, because we keep those, just the little lobby doors unlocked so that you can get to your work. So we want it to be convenient for you to be able to get to your work. But if we have to, we can take that convenience away. And so if we have to do that, it won't be something that makes it more inconvenient for us. It'll probably be a situation that, you know, lab notebooks would only be available after seminar when you catch up with your lab prof, or lab notebooks would only be available at lab lecture for you to receive them. And so, you know, if you're in a Tuesday lab receiving your notebook on a Monday, that's going to make things kind of tight for getting things ready to go for Tuesday, okay? So I want everyone to be aware of the situation. I'm hoping by talking about the situation that now it is ended. I don't want this to continue to happen, because if it does continue to happen, then we're going to just take away the accessibility you had to your graded materials, okay? The other thing to think about is, you know, this isn't the first year that these notebooks have been written. Like, organic lab has been happening for a while, and so people, there's other people that have taken the course. If you choose to look at someone else's graded notebook, now, albeit probably that is a situation where someone is giving you permission to be able to do that, think about it in terms of how you are helping yourself become a better student, and be really careful that you're not walking that fine line of, are you now going against academic integrity and cheating by looking at that information, okay? So be really careful how you handle the situation of looking at previous notebooks as well. If it's something that you're hoping to overall better yourself by doing that, and the person that you are able to look at that notebook from has given you permission, that's one thing. If it's, you know, you're taking their report and making it your own, that's completely cheating. That's not something that is acceptable behavior either, okay? All right. If you have any other questions about that, we can talk about it after lab lecture today. All right, so now on to some really exciting stuff. Hopefully you guys have looked at some of this in lecture. We are going to look at the Friedel-Crafts alkylation reaction this week in lab. And this is kind of all tied into your last big unit of what you're going to be talking about in lecture as well. And so if some of the things I talk about today you haven't necessarily covered in lecture, you will get there, okay? So listen to what I'm talking about now, and then listen even harder when you get to it in lecture this week, so that it reinforces what I'm covering, all right? But with this reaction, we're looking at something that is called electrophilic aromatic substitution, okay? So you've talked about alkene reactions. We've talked about forming alkenes in lab lecture, and you've talked about reactions with alkenes and how they will react with electrophiles. Aromatic rings are not as reactive as alkenes. So what you really need for this to happen is a really good electrophile. So some electrophiles that would react with an alkene will not react with an aromatic ring because they're just not electrophilic enough. Okay, and there's certain cases and certain situations that you can set up a reaction to be able to react or not with an aromatic ring. What you're looking at in this type of reaction is we've got some sort of aromatic ring, and we'll talk about potential substituents on the aromatic ring here in a little bit. And then we're going to react with an alkyl halide of some sort, and we're going to be in the presence of a Lewis acid catalyst to then get this alkyl portion to substitute for one of the protons on the aromatic ring. So in the end, you have an alkylated aromatic ring. Okay. And so here's an example. I'm going to kind of walk through a little bit. And this is something that is in your textbook as well, in the Frida Crafts section of McMurray. So we could have 2-chloropropane, and our Lewis acid is aluminum chloride. We could use that aluminum chloride to help dehalogenate our 2-chloropropane, so then we form this carbocation. Okay, so that's what our Lewis acid is helping us do, is form our electrophile, form our carbocation. Then that carbocation is going to go on and react with our aromatic ring. Now, a couple things that are going on here as far as forming that carbocation. You kind of have this in-between step. Where you've got partial positive charge here on where the carbon where that halide is coming from, and you've got your chloride kind of between, or your halogen between the organic compound that it was bonded to, and then also being attracted to that Lewis acid. Okay, and then when it completely reacts, you then get your full carbocation that is formed. Plus, in this case, the chlorinated form of our Lewis acid, so a chlorinated aluminum chloride. Now, another thing that's really important with these reactions, and anything that we're talking about with reaction directly on an aromatic ring, is the aromatic rings provide resonance with our 6 pi electrons on our aromatic rings, on our benzene rings. And so these electrons can flow around the ring depending on what's substituted and form different resonance structures. So in this example, we've got our carbocation was reacting with our aromatic ring, so the electron flow is from aromatic ring to the carbocation. And then we form this carbocation on the aromatic ring. The aluminum chloride then goes on, and basically we get aluminum chloride wants to be AlCl3 again, so we get it to take a proton from the aromatic ring, which will then form the HCl gas that's given off and then regenerate our Lewis acid in the aluminum chloride, and then we've got our alkyl group has now substituted onto our aromatic ring. There are other resonance structures of what happened here. So these are other possibilities if we move the electrons around the aromatic ring of the different types of resonance structures that can form from this alkylation. All right, and so we'll talk about these resonance forms here in a little bit and how they come into play for what actually happens on the aromatic ring. Now, we are going to use for our own specific reaction, we're going to use toluene. So we're not just going to use benzene, but we're already going to have an alkyl group on our aromatic ring, and the alkyl group we're going to use is toluene. Pretty bad. And the reason for that is this table over here. So the methyl group is known as an ortho para activator, directing activator. Sorry, wrong table here. Ortho para directing activator on this aromatic ring. So the methyl group itself has a little bit of electron density associated with it, and it's willing to use that electron density to help stabilize the positive charge that's going to end up on the aromatic ring as a result of this reaction. So we have chosen this specific substituent for that to help set up what we want to have happen in this reaction. And so in a minute here, I'm going to show you the different resonant structures that form because of the reaction with that methyl group. So we've got a couple different reactions that will be taking place in our labs this week. We're going to react our toluene with 1 bromopropane, and we're also going to be reacting our toluene with 2 bromopropane. Okay? And these alkyl groups are going to add onto the aromatic ring in a position, any position basically on the ring except for where the methyl group of the toluene is. Okay? So any of these other 5 positions are a possibility for addition. So with our propyl group, we could have ortho substitution. We would have a methyl group here. Our propyl group could add there. So with ortho, that's always 1, 2 substitution. So 1, 2. We could have para substitution. Which is 1 to 4, so 1 and 4. Or we could have meta substitution, which is 1, 3. And these 3 different types of substitution will take care of all 5 possibilities here, okay? Because there's 2 ortho positions, so there's 2 meta positions, and 1 para position to that toluene. Right? So just by doing the reaction of toluene with 1 bromopropane, we would expect that we would see some population of these different products. Not necessarily all equally populated, but some amount of each of these different products. Now, if we do the same reaction with the 2 bromopropane, we'll get the same type of substitution, but now we're going to have a branched alkyl group that is adding. So everybody see that so far? Just as possible products that could be formed, all right? Well, what happens is this is called an ortho-para directing activator. So that means that the methyl group is going to make it so that it's going to favor the ortho-para position over the meta position if you're looking at a kinetic process, okay, or a kinetically favored process. So let's look at the resonant structures for the different types of substitution. And so this is where the resonant structures that I was talking about earlier come into play. So if we've got toluene, and we have our secondary carbocation, okay? So our carbocation that was formed, this is our 2-propyl carbocation, and it works just the same for the 1-propyl, okay? 2-propyl carbocation. If we get ortho substitution, these are the 3 resonant structures that could form from that substitution, okay? So here we add at the ortho position, we get carbocation here. If we move the electrons, then the carbocation could move here in a resonant structure, or if we move those electrons again, we would get a carbocation here, right? With the para substitution, we would add at the para position, we would get a carbocation here, then another resonant structure would be a moving of electrons to get carbocation here where the methyl group is, and carbocation here on this carbon, all right? Now with meta substitution, so we've substituted at the meta position, we get carbocation that forms here, it can move to this position, and it can move to this position. What do you see is different about the meta substitution than the ortho and para? It's what? There's no tertiary carbocation, right? So we don't have a carbocation, a resonant structure where the carbocation is ever on the carbon where the methyl group is, which is a tertiary group, which usually makes carbocations happy anyway, but we also have talked about the methyl group having some electron density associated with it, that it will help by inductive effects allow that electron density to help stabilize what is going on with that aromatic ring. And so the electron density of this methyl group inductively helps to stabilize that carbocation on the carbon where the methyl group is also bonded to. Does everyone see that? So in the ortho case and the para case, that can happen. And so these would be the kinetically favored products, would be the ortho and para. Okay, so the products that would form immediately without equilibration of the system would be expected to be ortho and para. Okay? Now between the two of ortho and para, what would be favored more, ortho or para? Especially in looking at this guy here. Para, why? Sterics. So para is going to have an advantage over ortho because it gives more room for sterics and less steric strain because there's more room on the ring, not having a big substituent right next to the methyl group. Okay? So, we've kind of labeled these as our kinetically favored products, okay? Because of that inductive effect from the methyl group, and if we didn't have the methyl group there, the reaction wouldn't happen as well without that methyl group on there, okay? So we picked toluene for this reaction specifically because we want what that methyl group can help achieve with the reaction, okay, with its electron density. So then, with the meta substitution, what we typically will label this as thermodynamically favored. So when we're talking thermodynamically favored, what does that usually mean? What had to happen to get to the thermodynamic products? You've got you equilibrate to that product, okay? And usually is that going to happen warm or cold that you equilibrate? You're usually going to do that at warmer temperatures than colder temperatures, okay? So this is just based on what we're looking at with the compounds and what we know about the methyl group with these types of substitutions, what we would say would be favored for these type of products, okay? So we have kinetically favored and thermodynamically favored. Now this is what we're labeling them for now, but part of what the experiment is you're going to look at this and look at what really happens with the reaction, all right? So good so far. Okay, so now there's one more wrench to throw in the whole thing. Is what can happen with that one bromopropane. So if it just reacts and nothing changes with it, we would get the products we have drawn on the other side, ortho, para, and then meta. But let's look at the carbocation that is formed here. So with that type of carbocation, what could happen to that carbocation? And we talked a little bit about this kind of last week. We could get a hydride shift, and we could get rearrangement of that carbocation, right? And so instead of a primary carbocation, we could get a secondary carbocation out of it. Okay? And so besides looking at the substitution on the aromatic ring, another thing we need to look at is what did we start with and what are the final products. Okay? So one bromopropane can make these products without rearrangement. It can also make these products with rearrangement. So depending on what species of carbocation is reacting, we could get these products, or we could get these products, or we could get a mixture of all of these products, okay? Now what do you think would be conditions that would lend itself to this type of rearrangement? Thermodynamic, and would it be really cold or would it be really warm? Warm. Probably the warmer you make the reaction, the more you will see this happening, all right? And so what you can think about this as far as the carbocation, you can think about this as the kinetic, this guy as the kinetic carbocation forming that leads to these products, versus this being the thermodynamic carbocation that leads to these products. All right, so something had to rearrange and equilibrate to get to here if you're starting with one bromopropane. Now, with 2 bromopropane, do you think you would see the opposite occur? No. You're not really potentially going to see that a whole lot because there's no real advantage of going from a secondary carbocation to the primary carbocation, okay? But don't be surprised in conditions where the temperature's elevated a bit that you do actually see just a little bit of these guys form, because occasionally that will happen at the higher temperature when you use 2 bromopropanes. All right? But for the most part, you're not going to see rearrangement with 2 bromopropane, only with 1 bromopropane. So what we are going to do to look at this reaction and all of the different possibilities is we're going to divvy up the work. So what we could have you do is we basically have 4 possibilities for reaction conditions. We could run 1 bromopropane warm, 1 bromopropane cold. we could run 2 bromopropane warm and 2 bromopropane cold and make everybody run 4 reactions and gather their own data and figure things out. But we're not going to do that, okay? So you guys are each going to be assigned a specific reaction condition. So I'm going to put those up here, and your lab prop will tell you what conditions that you are running, okay? So this A, B, C, and D, though, is a standard label for this reaction. So when you are talking about different reaction conditions and you label it A, what I put down for A is that standard condition, okay? So don't, when you're discussing things, don't interchange these labels. These are going to be standard for everybody across all of the lab sections. Okay, so the A conditions we're going to do at 0 degrees, so an ice bath. And we're going to use 1 bromopropane, that condition, okay? And so with the 1 bromopropane, you will get substitution of the primary carbocation in either the ortho, para, and or meta position, and you potentially will see the secondary carbocation adding in the ortho, para, and meta position. For conditions B, we're going to do them at reflux, and we're still using our 1 bromopropane. And so you get the same possibilities. Ortho, para, meta. Ortho, para, meta. I'm trying to actually bond these together here. Then the C conditions are 0 degrees, but you're going to start with the 2 bromo propane, and so all you will see, for the most part, is probably secondary carbocation adding and the 2 propyl products. Then for conditions D, you will be doing the reaction at reflux with 2 bromopropane. And for the most part, these will be the type of products that you see. Although, like I said, don't be surprised if in a very small amount, you potentially, every once in a while, someone will see a little bit of the 1 bromo adding. But it'll be like 0.5%, nothing really, or even less than that, a really insignificant amount. So what's going to happen is we're going to give you guys these assignments in lab this week, and then we're going to give them to you in groups of 4, okay? So each group will have each of these conditions, and then the data that you're going to use for putting the tables together, you need all of the reaction conditions, so you're going to get the data from 3 other people in order to put those tables together. Okay, so it'll be the kind of the group that we put together of you. So be careful in running the reactions this week, because 3 other people are counting on you for your data and not getting something that doesn't make sense, okay? So be really careful in what you're doing this week, because it's not just your reaction, it's 3 other people need your data to make sense for them in order to do the analysis. We will be using GC for the analysis, not GCMS. So if you have an older lab manual, it talks about GCMS. We will be using gas chromatography, just like we did with experiment 8 and 11. It's different conditions. So that table that you copied off the front of the GC for 8 and 11, there's another table for 14. Make sure this week you write that down in your lab notebook. And what we will be giving you is your original data, and then in some form, the other 3 people's data as well. Okay. Then there will be, just like with experiment experiment 811, there'll be standard retention times. So the standard retention times are for toluene. And then basically the 1 propyl products and the parapropyl products. So it'll be a list of 7 retention times that you'll be given by your lab prop, okay? So use those for analyzing your data as well as the other members of your group's data. For your pre-lab, you want to show all 4 sets of conditions, which it's not, I mean, you just have to show the reaction 4 times instead of once. It's not a huge deal. But what you want to do is in your physical data table, make sure that you have both 1 bromopropane and 2 bromopropane in your physical data table as well, okay? And then next week, we will go over their tables on pages 14.9 and 14.10 in your lab manual. We're going to talk about those tables next week in lab, or in lab lecture. And these are the tables that you're going to prepare for your lab section before lab next week so that you can have an appropriate data comparison and data discussion for experiment 14, okay? So make sure that you get those tables together before you come to lab next week and have all your information together, okay? Because we don't want, you know, just one person in the group to get everything together for everybody else. Everybody needs to do it. Part of the reason we're having everybody do it is then that's the double check for everybody, is you should get agreeable tables if you're within the same group. So you want to make sure that your data makes sense and agrees, otherwise something's not quite right with calculations and so forth. Okay, let me show you. We're going to use kind of a different apparatus for the reaction this week. And this is shown in your lab manual as well. So everybody is going to start with this similar apparatus. You're going to start with your 250 milliliter Erlenmeyer flask. You'll put your 1-inch stir bar in there, and you're going to have your number 6 stopper that doesn't have a hole in it. So it's a solid stopper. That's the only reason that solid stopper is in your drawer, is for this reaction, okay? So that one solid stopper that's been floating around in your lab drawer the whole semester, it has come to be needed now. And you'll set this up on top of your hot plate stirrer, okay? You want to make sure you clamp. This is your reaction flask, okay? So this is where the reaction is going to take place. This portion of the flask is the condenser, which is going to come into bigger play for the people doing the reflux versus doing it at cold temperatures. But basically, if you're doing reaction at reflux, you don't want it condensing beyond this area on your flask. And you can even put a cold paper towel around that portion of your flask to help with the condensing, okay? Then you're going to have rubber tubing connected to a funnel. And you want to have kind of a dip in this rubber tubing. You want to make sure that the tubing is really dry before you set up the reaction. Aluminum chloride wants to react very well with any water. And so you want to make sure that the aluminum chloride doesn't react with water that's in your apparatus, all right? So make sure that everything you're setting it up is very dry. And then you probably want to put a little bit of dip in your tubing. That's kind of the last ditch kind of trap for any muck coming back into your reaction flask, especially for the people that are heating. So if you heat too vigorously in the reflux, you'll get it refluxing through the tubing, and you'll get that black muck coming back into your reaction, which you don't want to have happen, because that'll make your GC analysis a lot more complicated than looking at 7 compounds. Then you want to clamp the tubing up above this funnel, and then you're going to have the funnel inverted in a beaker about half full of water, and you want the water just about 1 millimeter above the lip of the funnel. So the reason we do this is we have an acid trap now on your reaction, because you're going to be generating HCl and HBr gas from your reaction. So we need to trap that. We don't want to just have poofs of gas going on in your hood. Those aren't things that are good for people to inhale and so on and so forth. So we're trapping it so that it doesn't just sit there flying around your hood, all right? And then people doing this reaction at 0 degrees will then have a pan of ice around their reaction. People doing this reaction at reflux will then have their reaction directly on the hot plate, okay? And in your lab manual, there is differentiation between doing the reaction at reflux or at 0 degrees, how you set up the reaction, and also under what conditions you're adding your aluminum chloride. So the reflux people, you will add your aluminum chloride at room temperature. You don't want to be adding it hot. And then after you've added it and stirred it for a period of time, then start heating. The people doing the reaction at 0 degrees will set it up immediately with an ice bath around their reaction and be adding the aluminum chloride when there's ice in their ice bath, okay? So make sure once you get your assignment for what reaction conditions you're using, you make sure you understand what you need to be doing with the setup and how you need to be heating or not heating things appropriately, okay? But if you are doing this at reflux, just be very careful with the heat. It doesn't take a whole lot to directly on a hot plate react a mixture of toluene and aluminum chloride and an alkyl halide, okay? Now, for this reaction, toluene plays two roles for this guy, okay? So we talked about it as a reactant. What is the other thing that toluene is doing for you for this reaction? It's your solvent for your reaction as well. So it's the reactant and it is the solvent, okay? So besides looking at what you need to for the specific reaction conditions once you get them, then you want to look at the workup, what is involved with the workup for each set of reaction conditions, okay? One of the things that you're going to use is concentrated HCl, and you're going to dilute it a bit and use this to quench your reaction. So be careful in handling the concentrated HCl and follow the directions in your lab manual for making that dilution, okay? Once you are all done with the workup steps, you'll be drying everything with magnesium sulfate. Be careful with this step, because one of the things we want to keep track of is how much product we've made in this reaction, and the way we're going to do that is weigh the reaction mixture at the very end and figure out what percentage is toluene and what percentage is product. So we don't want to change that percentage at all. So you're not going to be rinsing that magnesium sulfate with anything, okay? So when you go to use the magnesium sulfate, make sure you're using what you need, and then filter it carefully, but don't rinse with any toluene, all right? So it's going to be a lot like your experiment 11, drying your alkene. You're not going to rinse that magnesium sulfate, all right? After this step, then you're going to weigh your reaction mixture. And you're going to use that mass as well as the percent products that you get from the GC data to figure out how much of this total mass was actually product, okay? So you'll get your GC data, and it said, you know, you've got this weight, and it says once you calculate all the possible alkylate toluenes, that it's maybe, you know, 15% of it is actually alkylated toluene. So then you'll figure out what 15% of this mass is, and that's how much product you actually make. All right? But do make sure you record this mass after the workup before you do anything else with it. Yeah.
From there, are we going to need to analyze how much of that 50% is each different isomer?
Yeah, that'll be part of the tables that you go through. Yes. So we'll talk about all those tables next week. Yeah. So besides the weight, the other piece of analysis that you're going to use is the GC analysis. Okay. What you want to do is take 2 drops of your reaction mixture, and then you're going to, we're going to use pentane again for our solvent for GC. And remember with GC, we want to make sure, looking at the GC vial, there's no solid and no trace of water in that GC vial. So make sure before you submit your GC vial for analysis, make sure you don't see any solids floating around, make sure you don't see any trace of water, because that's really bad for the GC column. You can use the GC vials that you got back in lab last week from experiment 8 and 11 that you were supposed to clean out last week. Use one of those clean vials, and you can put a new cap on it and use that for the GC analysis. So change your ID on there too, okay, the sample ID. And what I'm going to have you do for the sample ID is I want you to give the initials, your initials, and then notebook page, and then I'm going to have you put the letter of your reaction conditions after that, okay? So that will help us for preliminary analysis of your data before we give it back to you. So if I was running reaction C, this is the sample ID I would want to give for my GC, is initials, notebook page, and the reaction conditions letter, and that's it, okay? So nothing else, no drawer number, no experiment 14, nothing else, just initials, notebook page, and reaction conditions, okay? Now, in the workup, one of the things that it talks about is you may get what is called an emulsion. And so an emulsion happens when you've got, you're going to be separating things in your separatory funnel. Emulsion happens when you get your organic layer and your aqueous layer, and they don't quite separate out, and you get kind of this middle layer. It's almost like it looks like a third layer in your separatory funnel. The solution to getting rid of that emulsion is to use saturated sodium chloride solution, okay? And so that will be available for you in the reagent hood. So if you get that emulsion layer, you want to use the saturated sodium chloride solution for your aqueous, the aqueous portion of your workup. Okay, so if you get an emulsion layer from the get-go, when you go to wash, tells you to wash with water. Instead of washing with water, wash with sodium chloride again. Okay, and avoid just the plain water. All right. So this is kind of hard to explain, but once you see it, you'll kind of know what I'm talking about, and then use what's in your lab manual to help you with that part, okay? So to help you guys out a little bit with your pre-lab, I'm going to give you, since I'm having you write a pre-lab for 4 reactions, I'm going to give you some of your physical data table information. So for 1 bromopropane, the molecular weight is 123 grams per mole. The density is 1.353 grams per milliliter. And the boiling point is 71 degrees. For 2 bromopropane, molecular weight is going to be the same, 123 grams per mole. Density is 1.31 grams per milliliter, and the boiling point is 59.4 degrees. Okay? So you can get that information copied. Now, final thing is, so in going with our final exam that's in 2 weeks, at the back of the lecture hall, I've put the practice exam for the final exam. So what I want you guys to do over the next week is work on the practice exam. The other part of lab lecture next week, besides going through the data analysis that you need to go through for experiment 14, is I'm going to go through that practice exam. The best way to know what you know and what you don't know with that exam is to have tried to take the exam before you come to lab lecture. So I'm going to give you the answers in lab lecture, but you want to try and take the exam before you come to lab lecture next week, so you know what you need to study and learn.